So let's look at the first colligative property, which is called vapor pressure lowering. This just says that the vapor pressure of a solution is lower than the vapor pressure of the pure solvent. So if you look here on the left, we have some salt water, and here on the right we have some pure water. So if we start on the right, you'll see that all these little red dots are water molecules. Okay, the water vapor exists above the liquid, and there's quite a bit of water vapor there. And if we look at the solution, we'll notice that there's less water vapor above the solution, because what happens is the sodium ions and the chloride ions attract the water, and it makes it harder for the water to escape. So since there's this extra attraction between the ions and the water, fewer water molecules escape. So since there's more water vapor here, it has a higher vapor pressure. Okay? And here there's less water vapor, so it has a lower vapor pressure. And that's really all there is to sort of why it happens. We can actually calculate the vapor pressure of our solution using something called Raoults law. Okay? This PA is the vapor pressure of the solution. Okay? PA, kind of this prime, is the vapor pressure of the pure solvent. Okay, and that's usually just found in a table, right? Remember, we have all those vapor pressures of water at different temperatures. And then remember, this is mole fraction. Now, the one mistake that students often make is they don't remember that it's mole fraction of solvent. Okay, so it's going to be the mole fraction of the solvent in the solution, not the solute in the solution. So let's try a problem and see if we can. So I want to calculate the vapor pressure at 25 degrees Celsius for a solution made with 97.4 grams of sodium chloride, 453 milliliters of water, and I know the vapor pressure of pure water is this. Okay, so the first thing I'm going to do is I'm going to remember that my equation is PA is the mole fraction of A, which is your solvent, PA 0. So first thing I want to do is find the mole fraction of the solvent. So I'm going to start by finding moles of things. I have 97.4 grams of sodium chloride. So I'll go ahead and do grams to moles. Sodium chloride's 58.44. So that's going to give us 1.67 moles. Okay. And then for the water, I have 453 milliliters of water, but that's the same as 453 grams of water. So I'll go ahead and change that to moles. Okay, grams to moles, 18.02 for water. So that gives us 25.1 moles. Now the trick that we need to think about here is, remember we just talked about Van Hoff factor, the I? Well, where the heck is the I? I don't see it. Well, it appears in the mole fraction. So the mole fraction of water is going to be moles of water, okay, times I. It's going to be I times the moles of sodium chloride plus I times the moles of water. Well, water doesn't break up, so its I is 1, so we don't actually care about that one. But for sodium chloride, I is going to be 2, because it breaks into sodium ion and chloride ion, so there's going to be a 2 here. So when we put all this together, we get 25.1 divided by 2 times 1.67 plus 25.1. And our mole fraction of the solvent comes out to be 0.883. Okay, which kind of makes sense. There's a lot more moles of water. Then we go ahead and plug into our equation, and we're almost done. So the mole fraction of water is 0.883. The vapor pressure of pure water is 23.76 millimeters of mercury. So if I do that out, I get 21.0 millimeters of mercury. So this is now the vapor pressure above the solution, and you can see that it is less than the vapor pressure of the pure solvent. And that's really all there is to vapor pressure lowering and Raoults law. So be sure you know what the colligative property is, why it exists, and how to do a calculation.